CC bond forming, just like before. Kind of cool. I'm going to do the abbreviated mechanism this time. This is an alternative mechanism that gets us in the same place without having to redraw everything a bunch. I'm just going to have this bond attack, because that's really what you're doing. That's the same idea. Because you have a pair of electrons, which is the bond, right? And that pair of electrons is attacking. So this, either way, either method is okay to represent this mechanism. I could have done that here also. I could have just had the bond attack. That's fine. That's okay. You know, either way is cool. I think the first time you learn this stuff, it's nicer to just think, oh, it's like an isolated anion, an attack. It's really kind of like a little bit of this and a little bit of this. It's kind of like both, but either method is fine for drawing mechanism. So whichever way you like. I think this is great because we don't have to redraw this with a C dot dot minus, you know. Okay, what do we get? What's our intermediate? Alkoxide. This time I'll skip the counterion because it's not really important. And I'll just do that. That's fine. Okay? Great.
Quick question.
Yeah.
When the C dot is on a benzoic carbon, I guess, is it more reactive than, let's say, the other one there?
I think it might be a little bit more. Yeah, they're both insanely reactive. Yeah. Yeah. There might be a subtle difference, but you can't really observe that easily. So. Yeah. Okay. All right. So that's cool. All right. Esters. Esters get attacked twice. R minus attacks twice. That's the difference between esters. There's a methyl ester of this molecule. Let's react this with methyl Grignard. Let's say CH3. Methyl Grignard. So, kind of like, remember with lithium aluminum hydride, how H minus attacked twice on esters? Well, in this case, R minus attacks twice. So, you attack once and you attack twice. So the first time it attacks, so we have a methyl Grignard, CH3 MgBr. First time it attacks, it makes a methyl ketone. So it attacks once, it attacks twice. And now this is another mechanism we're going to have to defer to later. It's not H minus. We're in CH3 minus, right? H3C MgBr. First step is essentially attack, and then details later. It's a little two-step mechanism. If you're in the lab, you actually learned this reaction already. It's nucleophilic acyl substitution. So the lab students will understand this because we had to teach it as part of the lab. But for now, otherwise, just wait. 5 chapters, and then you'll see that this. It's not that bad though. Okay, it attacks and it kicks off the methanol. That's the basic idea of this. The methanol gets released in this process. Now we have a ketone, and what do you think happens to a ketone in the presence of CH3 MgBr? It reacts again. It's just like we saw a second ago, right? We know that ketones are reactive. Let's just draw the line here. So it attacks again. ultimately, how many methyl groups got added? Two. Okay, so at this point, we can draw that as our mechanism. Acid, protonate, done. O minus grabs proton, you're done, right? Okay. And got aldehydes, ketones, now acids. We get really excited to do a Grignard with an acid, and let's say phenyl, Grignard. People asked me after class, I think last time, what pH means. I just want to make it clear that pH implies it's a benzene ring. It's the same as a benzene MGBr, right? That's the same as pH being MGBr. Which is the same thing, right? Just in case you are unclear about that. All right, so H3O, we get really excited to do this, and nothing happens.
Aww.
Aw, damn it. It sucks. That's you wasted $100. Didn't work. Damn it. What happened? Okay, so I'm going to draw out the Grignard now. That's the same thing. That's kind of an anionic structure of the phenyl Grignard. And I told you earlier, it's a nice nucleophile, but also a nice base. So here, its basic chemistry is going to do something. What's it going to do? Take the proton, and it's going to, you're going to destroy it. You're going to destroy your Grignard reagent now. Yeah? So your Grignard gets destroyed in this process, and you're out of luck, basically. Now, in most cases, and like you know, there's other things that can happen, but at least in our book, we just show this be our stopping point. You can't really continue here, right? So what happens when we treat this with acid? You have a carboxylate, O minus. Now you're just going to reprotonate, and you're done. All right. So that's kind of the end of the road for this reaction. All right. Cool. All right. So we got that one. So acids, pretty much, at least in this course, the way we teach this, acids are non-reactive. You can't do Grignard chemistry with acids, but you can do this ketones and aldehydes and esters. Those are the three things you can react with, right? Cool. Acid bad for Grignard. The conclusion here. Acid bad for Grignard. Carboxylic acids. All right, cool. One more. So we have one more that the book likes to call the formaldehyde reaction. And the formaldehyde reaction is simply say we have a Grignard, like an ethyl Grignard. Formaldehyde. Take your ethyl Grignard, throw in some formaldehyde, and out comes your molecule with one extra carbon. 2 carbons to 3 carbons in an alcohol. So it's just an easy way to add a carbon, all right, to a molecule. And so, of course, there's nothing magic here. The Grignard attacks the aldehyde. So it's a 1 carbon building block. That's what's cool about formaldehyde. It's a 1 carbon building block. And we just extended our carbon chain by 1 carbon. HBO. And that's all we did. Okay. So if we're presented with this kind of synthesis problem or test, we got a 6-member ring with a carbon and an oxygen, and we want to convert it to a 6-member ring with 2 carbons and an oxygen. This is not a very difficult problem. We can just do what? All we got to do is convert this to a Grignard. Convert the starting alcohol to a Grignard. PBr3, magnesium. Yeah, then we can just do this formaldehyde business, right? So we could do this in the forward direction, or we could do this in the reverse direction. We teach both of these methods. Sometimes I like to go the reverse direction. This is pretty easy to do in the forward direction. So let's just do the forward direction here, okay? So we got to make a Grignard, and PBr3, or you can do SOCl2 to make the chloride. Either of those is cool, but PBr3 is ideal. And magnesium. Okay. And you can fill in step 1 and step 2 at the end, which are obviously what we just did. So, okay. Okay, synthesis of alcohols via Grignards. Synthesis of alcohols via Grignards. So this is kind of just a little exercise in just kind of working backwards, I suppose. So the idea is, say I have this alcohol I want to make. How many methods can I employ using Grignards that would make this alcohol? Basically 2 methods, right? You have 2 methods you could use to build that alcohol, right? Because you're making, if we're using Grignard chemistry, we're making CC bonds, right? And so I could imagine making the A bond, or I could imagine making the B bond adjacent to the oxygen, right? I can make the A bond, or I can make the B bond, and that gives me 2 different complementary methods. If I'm making the A bond, how would I do that? So maybe the way to do that is get a piece of paper out and look at where the little squiggly line is, and I can imagine, well, obviously there's a Grignard side and a carbonyl side, right? Aldehyde or ketone side. So if I cover up like the right side, now I see, oh, now that makes sense. Now it's like a 6-member ring, 2 carbons, and probably Grignard, right? That's going to be the nucleophilic half of this reaction. And then the other side, I cover up this side, and I think, 3 carbons, oxygen, right? But you don't, okay, so what does a Grignard attack? a ketone aldehyde or ester, right? So when I see this 3-carbon piece, I kind of think aldehyde. Okay. There's already there's a hydrogen on the carbon. And that would make sense as an aldehyde. And if I attacked a 3-carbon aldehyde with a Grignard, I would make this. Okay. So what we're doing is kind of applying the Grignard reaction in reverse. All right. So this is what we basically concluded. Okay, that's our Grignard. This is the A method. And two steps. Step 1 is aldehyde, 3-carbon aldehyde. Right? 3-carbon aldehyde. That's the 3-carbon carboxylic acid. That would not work, right? Like an aldehyde. Let's draw the. That's a 3-carbon aldehyde. That would work. Okay? So we're using kind of that retrosynthetic analysis process right now. 3-carbon aldehyde, and what's my step 2? Just 3 of them. That would do it. Now let's do method B. Oh, sorry. Method B. Now you see the bond we're making in the method B format. Well, I'll show you the answer and then we can talk about it. But okay, so I cover up and where the squiggly line is, and I see that aldehyde, the corresponding aldehyde of this. So 6-member ring, 3 carbons aldehyde. And I'm going to actually draw that first this time, kind of arbitrarily. Here I do the Grignard first. You know, it is arbitrary. I'm showing either the Grignard being the nucleophile, or in this case, that being the electrophile. But now the question is, what's step 1 and step 2?
You want 2-carbon into the
Yep, exactly. Yeah. So we kind of cover up the right side. That shows the carbonyl we're attacking, right? And then I cover up the other side, and I'm like, okay, look at that. It's a 2-carbon nucleophile, 2-carbon Grignard. So ethyl magnesium bromide, 2 carbons, MgBr. And I could just say MgBr, H2O. That's fine. That gets the point across. Solution is reasonable to this problem. All right. So we have 2 methods. Now just notice I kind of said, well, here the Grignard, and then we're reacting with aldehyde plus acid. This actually is H2O or H3O. That's kind of a big deal. You can use H2O or H3O usually for these 2. But then in this case, I showed the aldehyde react with Grignard and acid. That's the order that I present these is irrelevant. Most importantly, though, the fact is that we have 2 different complementary methods that do the same exact thing. That's really cool. Okay? Neat. Okay, next. There's some more examples like this in the homework, so I would do a few all of them actually. All right. All right, so those are the methods to make alcohols. Now let's do some methods to react, reactions of alcohols. All right. Reactions of alcohols. All right. You can convert a tertiary alcohol to, RX, to a tertiary alkyl halide really easily. This is, I'm pretty sure you saw